Hello, welcome to another revision video. This is the second part. We'll go through the last two sections of this unit, so hopefully you can use it and go through revision for your test.
You have failed me for the last time.
So this first part we'll be looking at basically how the total mass we're doing through a chemical reaction between the products and the reactants is basically going to be the same. And it goes back to our core idea of the idea that we don't really create or destroy energy, and the same thing goes for matter. We don't create or destroy the atoms. So if we take the actual total mass of the products and the actual total mass of the reactants, they should be equal to each other. But sometimes it can appear as things gain or lose mass depending on how we weigh the reactants and products. But actually there is no overall change. The number of atoms should be equal. And then from that we'll be talking about how we represent this using word and symbol equations and the idea of balancing equations to make sure that we show that all the number of atoms, the total number of atoms, is always going to be the same. So if you remember, our main character is still trying to get his friends out of this dungeon, and he's given another long clue where it's basically telling him to think about the change in difference, the difference between the masses at the start and at the end, and to make sure that he's thinking of the total mass and thinking about the parts that he can't see. And this is, of course, referencing to the atoms that are converted into gas that he might not necessarily see during the chemical reaction. And he's given 4 different chemical reactions, or 4 different little experiments to go through to think about what would be the difference between them, the beginning and the end. So we only were able to do 2 of these in class, but if you remember, one of the ones was creating carbon oxide by burning, or copper oxide by burning copper and oxygen. There was another one we added magnesium, and we reacted it with hydrogen chloride, which of course created the salt and released hydrogen gas. So for this one, the copper oxide, we would see an increase in the mass, or a positive change in the copper oxide, where for the other one, when we had the salt and release of hydrogen gas, we would expect the mass to decrease because we're losing some of that hydrogen gas. Then there are 2 other ones we didn't necessarily get to do, but it's a similar situation where they would be increasing mass or decreasing in mass. And so he thinks, all I have to do is use the numbers that are the differences between the 2 masses, and that should work. But of course it doesn't work that way. The door isn't necessarily going to open because he's not looking at the total actual difference in mass between the reactants and the product. He's only considering the change in the mass of the copper or the change in the mass of the metal that's reacting with the acid. And so we have to look at the total system, the complete reaction, and whether or not there actually is a change in the amount of atoms actually through the reaction. So that's what we're going to talk about. So when we have a chemical reaction, we have to remember that every single reactant, every single atom is going to become a product atom. So even though we might not be able to see certain products, those products have to have been built from the atoms in the reactants. And so if we measure the reactants and we measure the products, we have to make sure that we're measuring all of the products at the end in order to make sure that they are the equal mass of the reactants. So for example, here we have hydrogen chloric acid plus sodium hydroxide. That should create our salt, sodium chloride, and water. So in this situation, we're not producing any type of gas, so the system is a closed system. Right? Remember, everything should be about the same. So whatever this mass is, and whatever this mass is, they should be equal because nothing was really lost in another form. Everything's still going to be a liquid inside of our container. We also know that we're representing the equal number of atoms. So if we think of the number of total atoms, there's 2 hydrogens on this side, here and here, and there are 2 hydrogens on this side, which we see here and here, right? If we look at it in terms of our chlorine, our green ones, there's 1 chlorine atom on each side. In terms of the sodium, there's 1 sodium atom on each side. And in terms of the oxygen, there is 1 oxygen atom on each side. So we know that this is balanced because the number of atoms is the same, or they are equivalent. If the atoms were not the same, we'd have an unbalanced reaction, or if the number of atoms are not the same. And if that is the case, we have to go through the steps of balancing the equation. So basically we're not adding any extra atoms, and we're not creating atoms, and there's no way the atoms are disappearing. So the total mass for the products and the total mass for the reactants should be exactly the same, because the total number of atoms is the same. We would see that if we were to weigh the sodium chloride versus the mass of the hydrochloric acid and sodium hydroxide, and we mass the salt in the water, they should be equal in mass, because the number of atoms is exactly the same as well. Now, under a situation in which some product is becoming lighter, for example, when a gas is going to be produced, the initial product would be lighter than the reactants, but the total mass is still going to be the same. So calcium carbonate here is heavier in mass than the calcium oxide, which is produced, but it should be equal when you also include the total number of carbon dioxide that's also produced. So we go through this reaction, and we do produce some carbon dioxide. So if we take the total number of calcium carboxide atoms and the total number of atoms here, when we look at both calcium oxide and carbon dioxide, the masses would be the same. However, since carbon dioxide leaves the system as a gas, right? If we're doing this inside of a beaker, this will leave as a gas. The overall mass of just calcium oxide by itself would be lighter than the total mass of the calcium carbonate. So we have to make sure we think about both products together and whether or not they're equal in mass to the reactants. And so again, we could check this by trying to do a balancing. So if we look at one side, it has 3 oxygens represented with red. The other side also has 3 oxygens. We have a single carbon atom on one side, and we have a single carbon atom on the other side, and one calcium atom and another calcium atom. So even though the overall product of calcium oxide will be lighter than our reactant calcium carbonate, if we include the carbon dioxide that's produced, it's still balanced, it's still equal in mass. So the total mass actually hasn't changed. There's been a 0 change in mass when we look at this reaction. If we go through the process of reacting a copper or a metal with oxygen, you remember that metal plus oxygen creates a metal oxide, right? And so here's where one of the reactants is going to be a gas, and when that gas reacts with the other reactant to create our product, we see an increase in mass compared to the one reactant we had. So copper is going to be lighter than copper oxide. However, if we think about all of the oxygen atoms that were floating around that copper, okay, that reacted with the copper oxide, the copper and the oxygen is going to be equal to the mass of the copper oxide. And we can check this as well looking at just the number of atoms present. If we've got 12 oxygen atoms on one side, there's also going to be 12 oxygen atoms on the other side. If we've got 12 copper atoms on one side, on the other side with the copper oxide, there will also be 12 copper atoms. And so again, since the total number of atoms is the same, the overall mass of the entire reaction is exactly the same. We haven't really changed anything. The copper has increased in mass by becoming copper oxide, but it only did that by taking the mass from the oxygen atoms, which are already part of the system. So this is when our main character is realizing that if you actually weigh all of the reactants and all of the products, then there really isn't a difference in the total mass. The total mass of the reactants and the products is going to be exactly the same. So then in the class you are given an opportunity to kind of assemble some of these equations and think about what is happening when we go through these reactions. And so, for example, we have a copper reacting with oxygen to create our copper oxide, and if we were to write a balanced equation, we would have copper plus O2 creates CuO, which is our copper oxide. In order for it to be balanced, though, we need to have double the number of oxygens so that we match our O2, but then it also means we have to double the number of copper ions as well. So we have to make sure that we've balanced our equation. With our other reaction, we had a magnesium and hydrogen chloric acid. So hydrogen chloric acid produced magnesium chloride and oxygen gas. So remember, that's metal plus acid produces salt plus hydrogen gas. And once again, we're going to have to balance it, where there are double the number of chlorines and hydrogens on this side, and so we add a 2 in front of our hydrochloric compound in order to make sure that it's even, so the number of atoms is going to be the same. Our lead nitrate was also reacting with potassium iodide to create lead iodide and potassium nitrate. In this situation, it looks like a relatively complex situation where we've got double the number of NO3, so that's what that means. And here we've got double the number of iodine, we've got just a regular K and NO3 on this side. But if we add up all of the atoms on both sides, really the only thing we have to do is add a 2 here and add a 2 here to make sure that we have double the number of the NO3 so that that balances out there. And we're doubling the number of potassium, so because that doubles there. And this also doubles the iodine, which is representative of that 2 there. So actually, if we look at all of the atoms together, again, there's no actual change in mass, and we have a balanced equation. And the last one is the breakdown of copper carbonate, which can create copper oxide and carbon dioxide. In this situation, it's already balanced. We have CuCO3, and it breaks down into CuO and CO2. And so the number of oxygen, copper, and carbon atoms are all going to be the same, and so there's no need to add any numbers to it. It's already balanced. So when we talk about these equations of explaining why the products seem to weigh more than the reactants and magically heavier, we know that we're adding oxygen atoms from the air to the copper in order to make our copper oxide. So the copper's mass is going to increase, but the overall change in the number of atoms is still going to be the same because we're just taking those atoms from the air around the copper. When we think about why is it less when we talk about magically lighter, one of the products is CO2. When we talk about this one here. And so since CO2 is a gas and can leave the system, all right, it can seem like the overall product gets lighter when we talk about our carbon oxide that's left over. But really, if we took all of the carbon dioxide that is produced and leaves into the air, the total number of atoms, again, is going to be the same. So if we think about what is going to be the keypad or the answer for our main character to get out of the locked room, well, since all the reactions don't have a change in the number of atoms, they would all be 0. There would be 0 change in the number of atoms, so there would be 0, 0, 0 is our code. And sure enough, if our hero enters 0, 0, 0, 0 as that code for the door, he eventually opens it and gets into the last room. So when we talk about balancing equations, one of the great examples of thinking about how we have to make sure we're representing all of the atoms and in the right circumstances, and we think about the space shuttle. So remember that in order to launch a space shuttle into the air, we're going to be using liquid hydrogen and liquid oxygen as a fuel. And so when we add liquid hydrogen and liquid oxygen together, it creates water, which is H2O, and then it releases lots of energy, and that energy can be what directs downward, and so that pushes our spaceship up from all that energy that gets released. So we have to think about the mass of our spaceship, and we want to make sure that we're not wasting any of the fuel. So when we think about the formula for hydrogen, liquid hydrogen is going to be H2, so there's going to be 2 hydrogen atoms joined together. And we think about our liquid oxygen that's reacting with the hydrogen. Liquid oxygen is going to be O2, so there's going to be 2 oxygen atoms together. And so what happens if we do that reaction of hydrogen plus oxygen creating water, it goes through this process. And so we see the hydrogen and the oxygen atoms are going to mix, okay, and then we get H2O as they reassemble, as those bonds reform. But we have one of these lone oxygen atoms left, and there's no hydrogen left over for it to react with. So this little oxygen atom saying, what about me? Don't I get any hydrogen to react with? And so that means that we would be carrying a whole bunch of oxygen atoms that aren't reacting, and they're not getting to be used for anything. So that means they would be adding weight to our spacecraft, because unless we use that oxygen in order to create H2O, we're not going to keep getting energy out of this chemical reaction. So we have a bunch of waste product that's going to weigh our spaceship down. So we can't change the formula. Hydrogen is H2, oxygen is O2, water is H2O. We can't change the number of atoms that are represented in each of the reactants in the products. However, we can change the amounts of each one. So that's what we're talking about when we balance them. So if we want to balance this equation, we just need to make sure that we include double the amount of hydrogen gas so that we have enough of a balance with the amount of water that is produced. So since there's going to be 2 hydrogens for every oxygen atom, that means we're just going to have double the amount of hydrogen in the spaceship compared to the amount of oxygen that's in the spaceship. And so when they all completely react, we get a balance of the right amount of water being produced. They all get used. And so we all, every single one of them produces H2O or combines to produce H2O and release the energy that is necessary. So we don't have any waste atoms floating around or taking up space inside of our spaceship. Everything gets used as a product. And so what we do is we just balanced our equation here. Having double the number of hydrogens produces double the amount of H2O. But again, the number of atoms is the same. And so we don't really gain or lose any mass. The change in mass is always going to be the same. There's going to be 0. There's no change in mass because the number of atoms is the same. So when we talk about balancing an equation, we only do this to a symbol equation, by the way. You don't do this with a word equation. And so you think if you're just adding a number in front of the appropriate molecule, and remember that affects all of the atoms inside of that molecule. So if we're putting a 2 here, that means that we have double the number of hydrogen and double the number of chlorine. So here we've got 2 chlorine, we've got 2 hydrogen. It's doubling each element, or each inside that compound. And so with this, we've got 1 magnesium, and here's 1 magnesium. We've got 2 chlorine, and here's our 2 chlorine. And we have 2 hydrogen, and here's our 2 hydrogen. And so we have a nice balanced equation where all of the atoms are being used, and there's no leftover atoms produced from this reaction. So there we have a nice balanced equation where the change in the number of atoms is going to be 0, which means that we have a good balanced equation. So then to help practice this, you're given 15 practice equations here on page 16. We'll just go through all of these. So here we have aluminum bromine reacting with potassium, producing potassium bromine and pure aluminum. In order to balance this, we're going to have to put a 3 in front of the potassium, which is the K, and 3 in front of the potassium bromine on the other side. The second one is already balanced, so we don't need to add anything to it. The third one, we're going to have to put 6 and then 4 in order to balance this equation. For number 4, we're going to have to add 2 to the lithium chlorine and 2 to the lithium bromine. That is on the other side. That is our product. For number 5, if we add 2 to the hydrogen chlorine and 2 to the hydrogen bromine, we get a nice balanced equation. For number 6, this one looks a little bit more complicated. One of the things that you would have to remember, though, is that SO4 can be taken as a unit here as well. So you don't need to worry about the number of sulfur and the number of oxygens individually because they're always going to be grouped together. So you can take them as a single group. How many SO4s do we have? And so to balance this one, we're going to have to double the amount of cobalt bromide. Add 3, or put 3 in front of the calcium sulfate, and 3 in front of the calcium bromine, and that makes it nice and balanced. For number 7, we need to put a 2, and then a 3, and then another 6 in front of sodium fluoride, and that creates a nice balanced equation. For number 8, we need 2 for that manganese, right? And 6 in front of the hydrogen iodide, and then 3 for the H2, or for the hydrogen that is produced, and 2 for the manganese iodide. So this one's actually another larger, more complex one. For number 9 as well, again, our PO4 can be taken as one group because they're always moving around as a group. You just think about how many PO4s as a group do we have when we talk about balancing it. So it's going to be 3 for the sodium bromine and then 3 for the lithium bromine as well. For number 10, we just need to put a 2 for the lithium fluorine and we'll be fine. For number 11, hydrogen bromine is going to need a 2. And then the number of water, H2O, is also going to have to be doubled with a 2. For 12, we're going to need to put a 2 for the lithium nitrate. And for the lithium bromine, that's also our product there. For number 13, it's already balanced, you don't have to worry. But for 14, you're going to need to put a 4 for the sodium bromine, and then a 4 for the sodium hydroxide as well. And then for 15, the last one, you need to put a 2 for the sodium cyanide as well. And then again, this is another situation where the CN is kind of working as a group. Here as well, you can see it just as a group. so you can think of it in terms of the groups. Sorry for number 14 as well. HO here and HO here are also moving around in this reaction as a group. So you could just think of it as how many HOs do I have in order to think about balancing this equation. Okay, so hopefully you understand balancing equations. You're going to see it on your test, something like this, where you're going to be given an equation just like this page, and you're going to have to be able to think about the number of atoms on the reactant side and on the product side, and then you need to put in the correct numbers in order to have a balanced equation. Okay, now we move on to the last parts for our revision, looking at part 4, the fourth part of the unit. And here we're just kind of taking all this information and we're going to apply it to just one slightly more complex chemical reaction, which you guys remember was creating the snake, basically the magic snake appearing out of the powder. So our objectives for this is basically solving a problem using a bunch of chemical patterns. So using all this information that we've learned from this unit, from all of the chemistry units as well, can we apply this information to figure out what's going on in a... So if you remember, our hero finally gets to the dungeon and he finds Speck and Fizz locked up, and so they need to figure out what is happening with this magic trick, so to speak, where a magical snake appears out of nowhere, and they need to be able to explain it, what's happening in order to escape. And so first we need to really think about what is happening and to watch this trick and make some observations. So during this observation, they say that there's a tablet that went black and basically smells of toffee, smells of like burned sugar. Basically, that's what they mean. That there's a bunch of black stuff that kind of foams up during the reaction. And then we also notice that there was a flame during this chemical reaction. And so they need to think of, what does all of this mean? So based on these observations, can we figure out what type of chemical reaction might be happening here? And this is a really good practice for something that could be like a 7-8 level question on your test. If given a bunch of information about a chemical reaction, can you figure out what type of chemical reaction, what general reaction must be occurring, thinking about the products and the reactants that are shown? So in class we kind of went through a list of general things that we have learned about chemistry over this unit, and think about whether or not they apply to our observations. So the first one, looking at an acid plus a carbonate will produce a salt, carbon dioxide, and water. So we know that carbon dioxide is a gas, and so one of our observations was bubbles. So we know that maybe this could be something that is occurring during our chemical reaction. Maybe the bubbles are connected to the release of carbon dioxide. Next, we're looking at acid plus a metal produces salt and hydrogen. So we also learned that one really well, right? We know that, again, turns into a liquid, so we could take the acid and it could dissolve, the metal could dissolve into the acid, creating a solution, so it could be a liquid is formed from the solid. And then we also have bubbles as well as hydrogen gas. So maybe this equation or this information is necessary in order to understand what's going on when the snake appears. Next, we have that carbonates will decompose when you heat them, and they will give off carbon dioxide. So once again, we've got bubbles. If we've got something that is burning or breaking down with heat, it could also be what's turning black. And then again, the idea that it burns or that heat is going to be released or it's a combustion reaction. This might be useful information when we look at what happens with the snake. Next, we have acid plus an alkali produces salt in the water. None of that is really useful to the observations that we've made, even though that is interesting chemistry and it is true. It's not necessarily going to tell us anything necessarily to what is going on with our chemical reaction with the snake. Then we have that solid metals. When you heat them, will turn back to solids when they cool down, so that they will melt and then change to a liquid, and then they can change back to a solid. So this might be useful in the sense of something could be burning, so when we heat them, we might burn it, and the idea of stuff turning into a liquid. Now, when it cools down, it might change back to a solid. Maybe not super useful for our example, but the first part, the idea that burning burning a solid that melts into a liquid, that could be a useful observation. Next, we looked at that the total mass of the reactants is the same as the total number of products, and that could be really useful when we think about the idea of something getting bigger. Though it may gain in size or may seem to get bigger, its total mass should be equaling to the total number of reactants that were used. So depending on how big the product is, we would have to think about where are the reactants coming from. if we are reacting it with oxygen gas, if we're using a combustion reaction, and oxygen gas is being added to our product, we think about what is the mass of all those oxygen atoms that were used. Next, we have the idea that fuels give off heat when they burn. Of course, that's going to give us the idea, or support the idea of burning objects will release heat, and then sometimes, again, things when they burn typically will turn black. So maybe we're looking at a combustion reaction happening when the snake is produced. Next, acids have a pH lower than 7, and alkalis have a pH higher than 7. Though, again, great, it's not super useful for the observations that we're making today. We don't see anything really about acids and bases in our observations for this chemical reaction. The next one says when as a gas is made, we can see bubbles in the liquid producing the gas. So again, we have come back to this idea of bubbles. So the bubbles are probably supporting the idea that a gas is being produced as a byproduct. So the production of bubbles or bubbling material shows that a gas is being released. Carbon dioxide turns lime water cloudy. Again, unless we were able to react this material with lime water, we don't necessarily know that carbon dioxide is necessarily the gas that's being produced. So it could be useful here, but we'd have to also do a lime water test to really know anything. And then last we have hydrogen gas burns with a squeaky pop when it is lit by a splint. So again, the idea of a gas that causes burning or is able to detect through burning. So if we are producing a gas that burns, that might be an indicator that is hydrogen gas. So now we need to take all of this information that we have learned from this unit and then these observations and try to figure out what is happening during this chemical reaction with the snake powder. And then we are taking observations that were generally made about the reaction. So we know that as a carbonate decomposes, that it produces carbon dioxide. So if we're seeing lots of bubbling, a lot of gases being released, and that carbon dioxide was present when this material reacts, so that means we're probably dealing with a carbonate. And so the bubbles are probably what's causing the carbon to foam up. So as carbon is reacting with all this carbon dioxide gas that's being released, that's what's probably causing the foaming material that we're seeing. We also see that fuel is being burned in order to produce heat. So sugar, for example, it probably is what's melting and burning to release the carbon that's locked inside of that sugar. And then we also know that it's getting bigger, but the total mass of the fuel and the powder together should equal the total mass of all of the gases in the snake. So if we're doing a combustion reaction, all of the oxygen atoms that are reacting with our sugar pellet and the alcohol that it's burning should equal the total mass of the snake itself plus the carbon dioxide that's also being released. So we all know that if we are writing this as a chemical equation, that the total number of atoms isn't going to change. So the total mass of the reactants and products, all the reactants used, all the products that produced would be the same. And so another thing that we talk about is the idea of how do we measure pH. And so we've already talked about universal indicator in an earlier lesson, and we know that the universal indicator will change to certain colors, a orange, yellow, red coloring for acids, and greenish blue, blue, and purple colors for bases, and a nice 7 for neutral, or green coloring for neutral. But there's other ways that we can test material. We don't necessarily have to use universal indicator because we might not be able to add the indicator to the solution or to the compounds that we're dealing with. So we'll know if there's a way that we can tell just simply is something an acid or a base without having to use our universal indicator. And it is added by the, I can't remember her name, sorry, that we could use litmus paper. And so litmus paper is actually just really simple reactive strips of paper that have a compound on it that changes coloring depending on if it's a alkali or a acid testing paper. So blue litmus paper is bluish in color. So here's this blue color here. And so that is the normal coloring. And if we put it into a solution and it stays blue, then that would be a base because there's no change. If we take the blue litmus paper though, and it changes red like this, or like a pinkish red coloring, that means that whatever it's touched is an acid. And so we can just easily test the solution real quick, see whether or not it's an acid, using this type of litmus paper. If we're not sure if it's going to be a base or not, we can take red litmus paper. So red litmus paper is like reddish in color normally, right here. And it will, if we put it in a solution and it stays red, then again, we're dealing with another solution that is also an acid. But if it changes to blue in color, like here, then it's going to be an alkali, and so that tells us that it's going to be a base. So then we were told to kind of write like a short summary and think about what are some things that we need to explain. So for example, why is there a flame? Well, obviously we are using an alcohol. Alcohol burns as the fuel. That's where the flame is coming from, the combustion reaction of burning alcohol as a fuel. And how is the solid tablet turned into a liquid? Well, if it's a solid and heated to high temperatures, it must be melting, and that's why it ends up as a liquid. The black material that is forming, that's coming from the burning of the sugar, so leftover burnt carbon material, this hydrocarbon material. It's not completely burning, not entirely changing into carbon dioxide. There is some burned carbon that is left over, and that's what we're seeing, and that's also kind of what we smell when the reaction happens. How did the black material froth up? How did it get all foamy? That's because then we released a lot of carbon dioxide from the bicarbonate that was used in the reaction. Why the liquid seems to disappear? Again, that's because it ends up changing to a gas. So as the fuel, the alcohol liquid burns, it eventually completely burns, changing into carbon dioxide and water vapor. So it changes into gases. And then is the snake really as massive than the tablet, really more massive? And we know that it's not, and that if we took the total mass of the added oxygen atoms and the total mass of the snake with all of the carbon dioxide that is released, that they would be equivalent to each other, because again, we can't create or destroy these atoms themselves. We're just adding more atoms that we don't necessarily see, and it's going to increase the size of our snake, of the product. So then it's saying, what could we use instead of the chemicals that were used in this demonstration? Well, we'd have to be using some type of carbonate. So maybe sodium hydrogen carbonate could be used, and that would be a solid material that can melt at high temperatures using like an alcohol as a fuel. And then, of course, being a carbonate, and will release lots and lots of carbon dioxide as a result, which could have the same effect as the chemicals that we did use. So then the last part is to summarize everything that we've learned from this snake experiment. And so the types of chemicals that must be inside of our snake powder, it has to have a carbonate in order to have lots of CO2 being released, and then it has to have some type of carbon-based molecule, mostly sugar, that can burn, a little bit as acting as a fuel, but really is supplying the carbon that is eventually forming the body of the snake, the black snake chain. What type of chemical is going to have to be in the fuel? Liquid, it's going to have to be a fuel. In this instance, it's an alcohol. It's a liquid fuel like alcohol, but we need some type of fuel. So it could be lighter fluid. It could be, some type of liquid fuel. Any liquid fuel would be fine. When the liquid is lit, what is happening? And then, of course, is that energy is being released in the form of heat. So as we're breaking the bonds in the fuel, and it's reacting with oxygen, doing our combustion reaction, all that energy gets released in the form of heat energy. So we see a flame, and then we also see that the solid sugar material starts to melt because of the high temperatures. So as the result of the energy being released, the carbonate is going to start to break down very quickly, and it's going to release carbon dioxide. The sugar is going to burn, and it's going to react with oxygen atoms in the air. And so the combination of the bubbling from the carbon dioxide being released, and then the sugar rearranging itself in order to create the long snake as this gas, this carbon dioxide gas, is released. And then it starts to cool down, creating that solid black material that is the snake. So generally, this is an exothermic reaction, so we know that the reactants have more energy than the products. And then, of course, that we see heat is being released. So we see a flame, and we can feel heat energy being released during this reaction. And ultimately, the snake looks really big, but if we were to take the total mass of the reactants, including all the oxygen atoms in the air, and the total mass of all our products, and with all the carbon dioxide that is released, they would be equivalent to each other. They would be equal in mass because we did not create or destroy any atoms. So the total number of atoms in the reactant side and the total number of the atoms in the product side are going to be the same. So the students, they explain this really, really well, and of course, They escape, the door opens, and it's now time for freedom to escape. But of course, the evil High Lord Pyro tries to stop them. But of course, they reveal him to be the bumbling old Uncle Boyle, and now they are going to overthrow him and prevent him from doing any evil in the name of the Pyros. And that is the end of our unit. So hopefully you understand everything that we've talked about for these last few revision videos. If you've got more questions, you can ask me in email or in class, and use all of this to help prepare yourselves for the test that comes up.